Okay, so we're going to talk about the mega rule. Thank you, Dave, for your introduction. Let me give you the agenda for this presentation. Today, we're going to talk a little bit about this PHMSA mega rule. PHMSA will have increased the requirements of the Code of Federal Regulations, Title 49, Section 192-150, passage of internal inspection devices. This particular section 192-150, it's an important section to make pipelines piggable. Then we'll talk about the new section 192-493. This is a complete new section, inline inspection of pipelines that will implement following the document one of the three documents that NISA will incorporate in the regulations. We'll talk about them in a little bit. And then we'll go through a clear example of how to follow these rules. 192-115 was already in the rules, but what happened with this is that now PHMSA has incorporated clear guidelines using the document, an ACE document, Standard Practice 0102-2010, inline inspection of pipelines, and it will give us clear guidelines to make pipelines piggable. Um, 192-493 means that when conducting inline inspection of a gas pipeline, you now must comply with the requirements and recommendations of three documents. These three documents are, the first one is NACE Standard Practice. We just talked a little bit about this, and this applies to new construction or planning of for planning of inline inspection survey. These documents establish design and construction guidelines for pipelines to accommodate inline inspection devices. Also in API 1163, this is the main document. It's an umbrella document that covers the NACE document and the third document, the ANSI document. And this is called the Inline Inspection Systems Qualification Standard. And it's an umbrella document because covers all aspects of inline inspection from planning to verification and validation of inline inspection run. And finally, the ANSI ASNT ILIPQ 2010, Inline Inspection Personnel Qualification and Certification. This gives us clear guidelines to verify the competence of inline inspection personnel, education, training, experience, and skills. These new three documents are in the gas rules since July 1st of this year. And the requirements are effective on this date. So what is the problem? The problem that we have until this now is that many of the pipelines were not piggable, and the ones that were piggable didn't have a clear standard of requirements to be piggable. That's what NACE document give us now. The other thing is that if you run an inline inspection tool, many of the runs before could have errors or problems in the data, and now you have clear guidelines to verify the quality of the inline inspection run from the beginning, from the planning till the receive of the report. Let me take you back in time, 55 years, to show a little bit of the problem that we have in the past. So let's go back to the year 1965, March 4, and it's 6:03 a.m. On March 4th, 1965, a high-pressure natural gas pipeline manufactured shortly after in 1945 exploded in Natchitoches, Louisiana. The flame escaping gas and explosion created a big crater 75 feet long by 30 feet wide. 3 sections of the pipe with a total weight of about 1,000 pounds were ejected as far as 350 feet away from the pipeline. 5 houses across the Natchitoches Country Club on Highway 1 were destroyed in the blast and fire. State police estimated the damage in that time, in 1965, for over $1 million. 17 people were killed, including 9 children. Several families escaped from nearby homes, including 9 people who were severely burned. 6 cars and 3 trucks were destroyed. This line have never been piggable. It was 1965. In 1965, in the same year, the first inline inspection was invented. Inline inspection tool in that time that was able to verify, to look for corrosion at the bottom of the pipe, only at the bottom of the pipe. Finally, some of the houses, of course, were completely melted, and a fire cremated area of almost 14 acres was left after the explosion. Before 1965, there had been other pipeline incidents before, but this explosion focused the attention on pipeline safety and led to then President Lyndon Johnson to call for the formation of a National Pipeline Safety Agency, which eventually would be created 3 years later in 1965. 10 years before this explosion, in the same area, just a few hundred feet away from this area of this explosion, the pipeline had exploded in 1954. So the moral of the story is expressed by the words of George Santayana. But let me rephrase a little bit those words and remind you that those who fail to learn from the failure history of their pipelines are doomed to repeat it. Because just in 2000, on Saturday, August 19 at 5:26 a.m., a 30-inch diameter natural gas transmission pipeline ruptured and exploded, reaching a temperature of 1,200 degrees Fahrenheit. The fireball was visible 20 miles away in Carlsbad, New Mexico. Before the firemen could get close, they had to retreat and wait for workers to turn off the flow of gas by hand. A family of 12 was caught in the fireball. 5 of them were young children. They were camping beneath this bridge. Only 1 victim would survive past the first few days. The force of the explosion created this crater, 113 feet long, crater 113 feet long by 51 feet wide and 20 feet deep. The crater was 700 feet away from the family that was camping beneath the river, the Pecos River, under a bridge. A 49-foot section of the pipe was ejected, and part of it was found almost 300 feet away. The pipeline was laid in 1950, and in all that time, this section of pipe had never been checked on the inside. And this pipeline, no significant corrosion was visible on the outside surface of the pipe. but in the inside was severely corroded in an area of 21 feet long. 10 years later, in San Bruno, California, a 30-inch diameter segment of an interstate natural gas transmission pipeline ruptured in a residential area. Approximately a total of 48 million cubic feet of natural gas ignited. It took 95 minutes to stop the flow of gas. It was a very long night. This is not a scene taken from a dystopian movie. The flames damaged 70 homes and completely destroyed 38 houses. 8 people were killed and 58 were severely injured. The rupture produced another crater, this time 72 feet long by 26 feet wide. A 28-foot long section of pipe that ruptured with a total weight of about 3,000 pounds, was found 100 feet south of the crater. This is the cross-section of the 30-inch diameter grade X42 steel pipe with a wall thickness of 375 thousandths of an inch. 375, and you can see the section in the inside surface of the pipe here in this area. And the section this is the area that was left without a weld, without being welded. This is a substandard and poorly welded pipe section, and the flaw was big enough to be detected by not by a corrosion inline inspection tool, but it could have been detected and measured by a transversal circumferential magnetic MFL, probably for the ultrasonic inline inspection tool or for an EMAT tool could have been detected, but the pipeline had never been inspected with an inline inspection tool. The failure is almost 50% of the wall thickness, the area that were not welded. It was supposed to be a fusion welded longitudinal seam. The outer portion of the longitudinal weld seam was welded. Here you can see this is all the area that was welded, but the area inside the pipe was left without being welded. The length of this area with this incomplete fusion was about 2.5 inches long, so enough to be detected by inline inspection tool. Okay, so, but this is not, of course, the problem with this pipeline have never been inspected, but it is not enough to run an inline inspection tool. You have to do it right. You have to choose the correct inline inspection tool for the threads and get accurate results with the inline inspection data. With the inline inspection tool, you need to have confidence. It is not a good idea to run an inline inspection tool that is not the best tool for the threads of your pipeline. In the same way, if you receive a report with thousands of anomalies, thousands of anomalies that you go and try to verify and you don't find them because there are false positives, well, that is not a good thing either. The only thing worse than a lack of inline inspection tool is to get the wrong results with the wrong inline inspection tool. In the past, the acceptance of an inline inspection run had been based primarily on the validation process, where the results of the inspection are compared to the results of field measurements. At best, the comparison can only show that the inline inspection run is consistent or inconsistent with the results collected in the field. The procedure does not prove that the inline inspection meets its performance specification. The inline inspection run is accepted unless evidence to the contrary is found once the verification firm has been completed, sometimes many months after the launching of the inline inspection tool, sometimes years, when it may be too late. So what is the solution? We need a systematic approach to clearly evaluate the results and the quality at each step of the inline inspection run, not just at the field verification of the results, during the whole process, and decide at any step whether the run should be accepted or rejected. And basically that's the API standard 1163. So we're going to show an example of the implementation, and the implementation is going to be divided in 3 parts. Pre-run, when you are doing the applying of an inline inspection tool, when you run the inline inspection tool, and when you get the results of the inline inspection run. This new process is systematic and consistent to ensure, consistent with 1163, to ensure that all proper procedures were undertaken by the operator when they choose the inline inspection, and from the vendor that provides an inline inspection tool that has specifications that will meet the requirements. The fundamental premise of the methodology is that a high quality inline inspection data is a consequence of technology, of consequence of a good planning and good execution. It consists of 10 checkpoints divided into 3 parts. These 3 parts, the pre-run, the inline inspection run, and the post-run, consider all aspects of the inline inspection run. So let's get started with the tool selection. And what are the documents that you're gonna require in order to keep this process traceable? So the first document basically is a form that will, once that you have followed these basic data, you will need to make sure that during the selection process, the main threat for your pipeline or possible combination of threats have been completely identified. So you need to target the anomaly, the minimum size of the anomaly that you are expecting. You need to consider the tool resolutions. The operator must review the tool performance specification, the specs of the inline inspection tool, to verify that the tool specs meet your requirements to detect the threats of your pipeline. Of course, the vendor tool performance specification must contain size inaccuracy, probability of detection, probability of identification, and confidence levels. And you will need to study those ones to make sure that they comply with your requirements. So how you do it? You will begin to check everything that passed, or the documents that are conditional, it has a conditional pass, and everything has to be passed in order to accept the run. Irregularities that have been found needs to be clearly notated. And a fail indication means that the data is compromised in some way, such as that the run cannot be accepted. So you cannot only, you will only be able to get to the next step until you have cleared all the fail annotations. And you have a record of those, and you have a total for all the stages for your for the analysis in each step: tool selection, performance, planning, so forth, until you get to the end, the tool validation and verification. So if you have a pass, indicates that the proper procedure was followed. In a conditional pass, indications indicates that some irregularities were found and you need to clear those ones. Let's go to the second step. So in this part, you need to choose to select the correct inline inspection tool. There are a lot of inline inspection tools available. MFL, circumferential MFL, ultrasonic, compression wave, ultrasonic shear wave, EMAT, elastic wave, eddy current, you name it. But which tool gives you the biggest bang for the buck? Which is the best tool for your inline inspection requirements? To choose the correct tool is not an easy task. It requires you to know the advantages and disadvantages of each technology. You need to know what are the threats of your pipeline, what are the combination of threats, what are the worst type of defect that you are expecting to find. And of course, it depends also of your parameters. Probably you don't want to run an ultrasonic tool in a gas pipeline if you're not willing to batch. Probably you need to comply with some requirements of flow speed, and probably you won't be able to use a tool because it's running too fast or too slow. Or even you have to ask yourself which vendors provide the best overall service and which one gives you the best data. These are very difficult questions, but you need to answer them before the planning of the inline inspection run. And the NACE standard practice SP0102 provides a great help with this table. Gives you anomaly types and the available tools to categorize your defects. And the selection of the inline inspection tool has also to be complemented with these two documents: the API recommended practice 1160, managing system integrity of hazardous liquid pipelines, and the B318S, managing system integrity of gas pipelines, which is more towards our operators today, which provides the information necessary. This document provides the information necessary to develop and implement an effective integrity management. But also you will follow this. This is an electronic table based in the in the NACE standard practice 012. And you will look for the threat. In this case, let's say that is metal in close proximity, or you have another pipeline that moves close to yours, or let's say that you're looking for paddle wells or for casings. Well, which is the best tool for that? So probably for in this case will be MFL tools that will be able to get metals in close proximity and even detect hard spots. So you will look for the inline inspection tool that is best for the type of threats that you want to look here. Once that you have the right tool for the job, you have to verify the system performance, the specifications. And the system performance specification, in many cases, for instance, you will decide to run an untested technology. Let's say that you have a new vendor that offers a new technology. This will require an ample and extensive validation before using the run results, because this is an experimental tool. In a similar manner, if you have not previously used a particular tool, you will need to request to the inline inspection vendor relevant documentation that demonstrate the successful performance of the tool with previous customers or with previous projects. Let's say after that, you will have to do a planning of the inline inspection tool. Now that you have verified the historical system performance of the tool, that you have selected the tool, it is time for planning. And planning, one of the most important things is to have the pipeline clean for inspection. This is one of the most important activities of any inspection, the cleaning. Cleaning targets must be met prior to put an inline inspection tool in the barrel. You need to do this because a pipeline like this will never provide a good data. The tool will be probably stuck, or in the best case, the data will not be valid. And of course, many technologies are more susceptible to debris or wax and dirt than others, but in general, you want to clean for inspection. Otherwise, your MFL tool will be a very expensive cleaning pig. And you will have to follow the procedure and also to make sure that the pipeline is pickable for the inline inspection that you are selecting. If you have a very short radius in bends, probably you cannot choose any other tool, but only tools that will be able to navigate in your bends. If you have 1.D or you have 3D or even less, you will need to choose carefully the inline inspection tool and make sure that you are using the correct tool. Especially field bends and river crossings must be reviewed thoroughly because some pipelines could contain tight radius bends and even miter bends. You have to be careful about unbarred tees and also back-to-back tees. These are very close together. Branch connections with 30% of pipe diameter or greater should have a scraper bars to prevent the pig to going into those offtakes. You have to make sure that valves are completely open during the inspection and there are no reduced port valves in your pipeline. And for that is key the pipeline questionnaire. It is important that you provide as much information as possible to your vendor, to your ILI vendor, to avoid problems and delays. Wall thickness is a very important parameter for which some tools need to be calibrated, especially MFL tools. You need to provide the amount of magnetization to a heavy wall in order to be able to detect any defect in those wall thicknesses, in those heavy wall thicknesses. Smaller diameter lines with heavy wall thickness are a very big problem for MFL tools because you have to magnetize these ones with very small tools. But you have to provide the amount of magnetic field necessary to saturate the steel in those heavy walls. Of course, you will also need more differential pressure in order to be able to move this heavy tool with the small diameter section. The next step is a pre-run preparation. So there are checks that you need to make sure that the vendor is doing, and probably you need to audit this verification in order to make sure that the inline inspection tool is in good working condition. This is a simple test, but very important. This is a 56-inch diameter MFL tool, and they are checking that that the sensors are moving correctly. So it's a mechanical check to confirm the mechanical integrity of each sensor prior to the run. So this one is in the workshop, and you can go there and audit that everything is tested in the way that guarantees that you will have a good inline inspection. So there are also mechanical checks, but there are also functional checks. These checks are somewhat specific for each technology and vendor. And for this reason, you will need to complement this list with a functional checklist provided by your vendor. So he will need to provide you a checklist well in advance to your run that you will be able to follow to confirm that there is, for instance, available power supply on the tool, that you have all the sensors working, that you have data storage in the tool, etc. So after the checks, you will need to do the execution of the run. And this is where the fun part begins. This is not time to take a break and wait. There are a lot of things to do, and some of the things that you will need to do is to make sure that the inline inspection is working in the correct way. So in this part, in the run execution, you will need to make sure that all the markers are positioned on top of your pipeline, that the crews have been instructed and fully trained to put the marker boxes on the right-of-way on top of your pipeline to make sure that the boxes are triggered and they are the data has been downloaded. And then after the inline inspection, run execution, you will go to some checks after trapping the tool. So there is no time to celebrate, like Bob here. Bob here is celebrating too early. It is time to do some checks of the tool. And it's time to get your hands dirty and to make some checks. Also, again, mechanical checks and functional checks. Again, making sure that all the sensors are mechanically functional in the case of MFL tools, or they are operational, that the tool was in recording mode, that was not damaged, etc. And these records and these checks will help you to make sure that you have recorded good quality data. Again, here you will need a copy of the inspection mechanical and functional test presented by the vendor. In general, you will look for a visual inspection of the tool. How clean is the tool after being trapped? There are debris. Where is the debris? Where is any accumulation of debris is important because many sensors probably are not operational because of the debris accumulating in some areas. Wear and tear. Is the tool wear more than it should? You have to make sure that all the parts are intact after the inspection. And you will need to document this with photographs of the tool at the receiver in order to document this stage. And finally, data quality check. And this is really the important part of the process. And you will need to check the quality of the data in the field way before the tool is taken away from the field, because if the quality of the data is not good, you will need to demand for a reinspection. So you have to do a comprehensive check with a rapid scrolling through the data to make sure that the data is complete. In addition, you will have to look for the data to look for striking signals in the data to confirm that the data meets basic quality requirements. So you will need to create and request a report from the inline inspection vendors that ensure that the data has been reviewed not only for data completeness, but also plausibility. How possible is the data that you are seeing that corresponds to the actual data in the pipeline, with the actual conditions of your pipeline. The amount of data collected not only need to be completed, but has to be reasonable. The data appears to be what is in your pipeline. Do you see the joins, valves, fittings that you have, that you know that you have in your pipeline? Those are important questions to answer. And also the quality. How good the data is to be analyzed. Good, excellent, degraded. And this is important because a data that is degraded, data that is difficult to analyze, probably will cause false negatives. The analyst probably will fail to detect some of the features because the data is not really of good quality, but is degraded. It's difficult to see the features, it's difficult to see the anomalies, and that is critical. In general, you shouldn't wait more than 5 days after the inspection of your asset in order to receive the report indicating the quality of the data in these three categories: completeness, plausibility, and quality.
Hey, Bernardo, excuse me. We have about a few minutes till 10 till. I just want to make sure we're getting close to the end so we have time for questions. So just letting you know. Thank you.
Oh, thank you. Yes, this is the end. And after the analysis of the data, of the quality, we have to do the validation. And the validation basically gives you the unity plots. And the unity plots are where you compare how accurate the inspection tool and if it's within the confidence interval determined by your vendor. This will translate in a statistical analysis of your data. And in this case, you have to consider all the anomalies, and not only the ones that are within the specs, but also you need to consider the ones that were overcalled, like in this case, that are on the upper part of this unit plot. So you will need to consider all the anomalies to avoid this, to skew the data when you're analyzing the data. And of course, there are many anomalies that could be overcall in one category. In this case, on your right, this is the length versus the depth. And this feature here has been undercall in length, but has been overcall in depth. So you need to look at these together. And finally, let's review what this is meant. This is a systematic approach to look at all the stages during the inline inspection run. You have to assess all parameters taken as a whole. The big picture is what we're looking here, and determine if the tool performs within the requirements. And you will be able to stop the the process at each step of the process, because you will, if the tool has not been, if the run has not been executed in the proper way, well, you should not expect good results. So this is a question for you. Do you take the time to look at the details in the data using the vendor supply software provided by your vendor? Well, this is important because this is the only way to look at the data in the field to make sure in the field if it's plausible, if the data is reasonable. You have to take a look at, get familiar with the data. The time invested in each step of the line inspection gives you an important idea of your maintenance procedures, of the how safe is your partner. The time invested here is not wasted. This will minimize costs in the long run, will minimize costs of false positives or false negatives, etc. And you have to keep in mind that the true integrity of a pipeline is not really about what you found, what the tool detected. The true integrity of the pipeline is based on how confident you are that everything was detected, that everything that you decided not to verify is okay staying in your pipeline. This is the most important part of the integrity, is if you can sleep well after the inline inspection tool, knowing that you have decided not to respond to many anomalies because you know that the tool was reporting within its specifications. So with this, we'll open for some questions. I'll be happy to answer them.
Thank you, Bernardo. Yeah, like I said, if you have any questions, feel free to unmute and ask verbally, or you can also use the chat function and we can state the question to Bernardo.
I did have a question. This is Steve Howard.
Thank you, Steve.
Hey, you know, a lot of this is focused on the transmission. I guess from the gathering perspective, I mean, what do you see possibly bleeding over to gathering pipeline systems? You know, where there are a lot of class 1 in rural areas, but we do go through some, you know, some pretty tight and congested areas at times, but a lot of this is obviously driven by past incidents and the transmission industry being the primary focus. But, you know, we figure it's only a matter of time before, you know, the gathering pipelines are subjected to, you know, more regulations. But I guess, what do you see on the gathering side and maybe coming down the pike?
Perfect, very good question. Thank you. I believe that the gathering pipelines, operators in this type of pipelines that are difficult to pick, will benefit from the advances that has been for pipelines in refineries. And there are many piping in refineries and furnaces that now are being inspected. So the new tools, the new technologies are going towards being able to inspect 1D bands, or sometimes even less than that, but 1D is pickable now with many technologies. And with many what they being called unpickable pipelines, tools for unpickable pipelines. So I think that if you explore the solutions that have been available for refineries, and you will be able to find tools that will be able to pig gathering lines where the conditions are not perfect to pig, and also solutions with tether pigs, in which you will have to, in many cases, you will be able to pig without taking the line out of service. So I believe there are many advances in line inspection tools that have been toward other type of for other type of environments, not for gathering, because the regulations until now, there were no focus on gathering pipelines, but in refineries, where it's very important to keep uptime and reduce this downtime, and they have been able to inspect very challenging pipelines. I think you will have benefits from those parts of the market that have the same challenges that gathering pipelines have.
Thank you.
You're welcome. That is that something that will help you?
Yeah, I think that, as a company, we have, we inspect certain pipelines for reliability purposes, not, and so, just really understanding, not only the technologies, but also regulations that might drive more of that. Yeah, you covered some good analysis tools on, how to go about.
What are the other challenges that you can have to pig those gathering lines beside the tight bands? And
yeah, I think, some of the challenges that we've kind of overcome over time is just, simple things like pig barrel design, making sure the barrel's long enough for smart pigs, and making sure we design pipelines with, like you say, long bend radius fittings, and just from a design perspective, making sure we don't do things that are going to limit us in the future should we decide to drop a pig in some of these pipelines. So where it makes sense. Some of these lines are really short and it doesn't make a lot of sense, and some are again more akin to transmission type, long stretch pipeline. So
in the future, while we get more requirements to pig these gathering lines, the price of many of the solutions will drop because there will be more vendors attending the niche, and that will draw the prices down, and you will have more options like tether tools, and you will have more options also of diameter. Like now, smaller diameters are 3 inches to inspect, and probably there will be newer solutions and at lower prices as more gathering lines are being inspected.
Thanks.